So hi, folks. Today we are going to talk about adversarial machine learning. So let's go to the lecture. So I have outlined. Today we have 5 different parts. First part, I'm going to introduce what's adversarial machine learning, why it's important, why it's possible. And the second part, I'm going to introduce the techniques, the key idea of adversarial learning, how to attack, right? And then I introduce strategies. How can we defend the machine learning model from attacking, from hacking? So, and the next part, I'm going to introduce how can we effectively defend. I mean, can we further improve the generalization performance of machine learning model by using the defending strategies? And in the final part, I will introduce a conclusion. Okay, let's go to this lecture. So for the first slide, let me briefly review the regular machine learning. So the typical process of regular machine learning. So we have some training data here. The historic data is our training data. We use some machine learning algorithm like IGG, ADAM, or momentum IGG, or AdaGrad. And we have a neural network architecture like a ResNet, EfficientNet, or AlexNet. We use machine learning algorithm to train our architecture by getting the information from the data, and then we get our model, right? So after we finish the training, now we get a new data. We want to use our trained model to make predictions, to make decisions for the new data. So, and hopefully we can get a good predictions, and we output our score. I mean, score can be accuracy. I mean, yeah. That's the typical process of regular machine learning. So now let me give you a specific example to give you the idea of adversarial machine learning. So firstly, as I mentioned, we need the training data, right? Even for regular machine learning, we need the training data to train our model. So here, the first part of our training data images with panda. So for example, I got these images from internet. From human being, you can see clearly each image has a panda, right? So we can correctly label these images as panda, right? Okay. And also the second part of the images, the training data, are the images with gibbon. So I also got the image from internet. Clearly, you can see for each image there is a gibbon, right? Or two gibbons. So we can also correctly label those images as gibbon, right? Okay. I gave you, 2 parts of our training data. One part is the images of panda. The second part is the images of gibbon. But we also have some other different images like images of human being, car, rocket, supermarket, or many different kinds of images. But we can make sure all these images are correctly labeled. So we use this training data set, many images, to train our model. So here, the architecture of the model is GoogleNet. And we use the correctly labeled data to train this model. And after training, we want to make prediction for some new images. Our first new image is this one. For human being, what do you think? Clearly, it's panda, right? What do you think our machine learning model should make the predict? We know here I'm very confident our machine learning model was properly and carefully trained. What do you think the model will predict for this image? panda, right? It's the same as a human being. Because our model, I think, is well trained, so it can give you a good answer. So it has roughly 60% confidence it's a panda, right? So good. That's for regular machine learning. Okay. Now we get a new image. So here image 1, here image 2. Actually for human being, for human being, you can see image 1 and image 2. They are very similar to each other. It's very hard for human to tell the difference from them, right? So for human being, we label the first image as panda, right? And the same thing, we should also label the second image as panda, right? Because they are very, very similar to each other. How about the machine learning? What do you think the machine learning model will predict the label of this image? It's given? Seriously? I'm really surprised. So why? I mean, why machine learning model give a label of given to this image, right? And also the confidence is very high. That's ridiculous. I mean, the machine learning model is wrong, but with a very high confidence, that's stupid, right? So I'm totally surprised by this prediction, by the prediction of this machine learning model. I'm going to explain so why machine learning model gave this prediction, and how can we solve this problem later. Okay, to answer your question, so why image 1 and image 2, they are very similar to each other, and for human beings they are roughly the same. Why machine learning model gave them two different labels? So let's have a look at the comparison between them. Because the images they are saved into matrix or tensors in computer, right? Let's give you more details. So here I just want to make things easier to understand. We just assume each image is a matrix. So what's the difference between image 1 and image 2? It's the difference is a noise matrix, right? So here I give you the noise matrix. It's I mean no pattern here for human being, right? And also we want to make each element of this noise matrix tiny. So here we have a hyperparameter. Okay, so now the difference between here image 2, here image 1, the difference between them is this noise matrix. However, we know for human being we cannot tell the difference between image 1 and image 2. Probably the reason is this this part is too tiny for human to tell to tell the difference. Okay, let me firstly give you more example, and then we will explain why ML machine learning model cannot tell the difference. So the first example is panda. Second example, so here clearly for human being, it's a sports car, right? Sports car, and also a well-trained machine learning model can easily label this image as sports car. However, after we add noise, we get a new image. For this new image, it's still a sports car for human being, right? However, for machine learning model now, the output, the prediction is toaster. Seriously? I mean, it doesn't make any sense to me. Nothing, no toaster here for human being, right? Okay. Okay, the next example we have duck, and for well-trained machine learning model, it's also duck. However, after we add noise, again, for human being it's still duck, but for machine learning model now, the prediction is horse. That's ridiculous. It's it's I mean very different from horse, right? And also I mean I just gave you some examples for the computer vision application. We actually also have some other examples for I mean machine translation or NLP or the other language processing application. So here we get a signal. So for human being, it's how are you? And for well-trained machine learning model, it's also how are you? For example, if we human being, we listen to this signal, we understand it's how are you? And then we add noise to this signal, and we listen to it again. For human being, it's still how are you? But now for machine learning model, the understanding is open the door. That's interesting, right? they are the meaning between them are so different. That actually can be a serious problem in the future, because in the future probably machine learning system will be everywhere in your home. So we probably can use in the future we can use our voice to control many robotics in our home. If some bad people they hack the machine learning models in our home, that can be a serious problem, right? Okay. Now, let me give you a definition of adversarial machine learning. It's a new technique to make the machine learning model confused, to attack the machine learning model, to fool the machine learning model. How can you do that? They give the machine learning model some bad images. I mean, for example, bad inputs, for example, images, deceptive input. In this way, the machine learning model can be confused, can be cheated. So let me go over this workflow. So the first part is traditional machine learning. As I just mentioned before, we get training data. We use a machine learning algorithm like IGD or momentum IGD, or Adam to train our neural network architecture. After training, we got our trained model. We use our model to make prediction for new data, and hopefully we can make the correct decision or correct prediction, give the new data correct labels. But for here, for the adversarial machine learning, it's different. Now we get new data. The attacker or the hacker, they want to add noise to the new data. Now here is the data with noise. We refer to adversarial samples. So we gave the trained model the adversarial samples for prediction, and in most situation the model failed, and the machine learning model gave us wrong predictions. So that's the typical process of adversarial machine learning. So why people want to do that? Because I mentioned before, in the future, machine learning everywhere, they want to make your machine learning system crash, and they want to attack you, to bother you. That's bad, very dangerous in the future. So we need to defend the machine learning system. Okay. So why adversarial machine learning important? Again, I told you before, because in the future machine learning will be everywhere. But here, let me give you some example why it's important. For example, every day we will use a sperm classifier, right? So if someone can attack the sperm classifier, probably you will receive 100 or 200 sperms every day. It can lower your working performance, can bother you, right? And also, that can make your important email spam. You probably will miss some important emails. You will miss some important meetings, some important interviews. Can ruin your life, right? Ruin your career. So second application, for example, face recognition. So some people can attack a face recognition system. It can probably hurt your privacy. And also in the future, maybe the bank will use your bioinformation to protect your money. But some bad people, they probably can attack this bioinformation machine learning system, and they can steal your money. And also in the future, probably self-driving car will be everywhere. So actually, the adversarial machine learning can also attack the self-driving car. So here, let me give you an example. For this one, it's stop sign. So for human being, it's stop sign, right? For well-trained machine learning, it's also stop sign, correctly classified as stop sign. But however, if we add noise to the stop sign, we get a new image. But for this new image, it's still stop sign for human being. However, for machine learning model, now the prediction is not correct. It's error set. That's an example. Probably you have different technique. You can make the machine learning model to even more confused. Probably if you have other techniques, you can make the model to predict this as a speeding limit. That's very dangerous. It can kill people on the highway, right? Okay, let me give you another example. So for this image, clearly for human being, it's a traffic light with red color, right? So we should stop if we are the drivers when we see this. And for well-trained machine learning model, it's the same thing. It's also a traffic light with red color. However, if we add the noise to this image, now we get a new image. For human being, the same thing. It's still traffic light. We should stop. However, now the machine model make prediction for this as a hummingbird. It's very interesting because this image has a hummingbird, but it has more important thing, the traffic light, right? We should pay attention to the traffic light. So that can be very dangerous. If a self-driving car make predictions that it's a hummingbird, probably can kill some people because it's here in red, right? So I won't say the example actually use a very good neural network. It's Inception V3. It's probably the best several years ago. With a 99% confidence, it's a hummingbird. It's wrong, but has a very high confidence. That's stupid. Okay, so I give you many examples. I just want to show you adversarial machine learning is very important. We should make our machine learning system safe, and then we can use it. Okay, now let me explain. So why machine learning model can be confused? I mean, can be fooled, can be attacked by the bad people. Before I introduce that, let me give you some notations. So here for wx it and w tutor, they are n-dimensional vectors. So here I just want to make it easy to explain. So here I use w as a weight vector. Assume we only have one layer as a linear model. Just as an example in Goodfellow's paper. So eta is a noise vector, and x is one clean sample. X tutor is an adversarial sample. So here, epsilon is a small number to control the precision. It can be ignored by the numerical system, for example, by hardware. So it's a common thing in numerical computing. So why machine learning model can be confused? Why we can attack a machine learning model? Because often the input feature of an image is limited. For example, the digital images, they often only use 8 bits per pixel. 8 bits means 2 to the power of 8. You have 2 to the power 8 is 256. You have 256 different different types of information. So so here assume every element of eta eta is a noise vector. Every element of eta is smaller than the precision, and also because this precision is limited, is very limited. So we expect so the model cannot tell the difference between x and x tilde, right? So I mean, here we assume every element of eta is smaller than the precision, which means the infinity norm of eta is smaller than eta, right? So why we expect that the model cannot tell the difference between x and x tilde? Because for human being, when we see a picture, we see the picture a block of pixel by a block pixel. For example, a picture of a human being, we see the head, the arm, the body, and the eye, the mouth, and we make a prediction that's human being, right? So a pixel, we actually see a block pixel by a block pixel. So if every noise, I mean, we actually now here we add a noise vector to the image, but for each pixel, the incremental part is very tiny. So for human being, it's nothing, right? So we for well separated classes, we expect the model to assign the same class to x tilde, because every element, I mean the change in every element is too tiny to tell the difference for human being. However, for machine learning models, they actually use a different way to make prediction. For example, the one layer machine learning of one layer deep learning model or one layer neural network model, they use activation. They make prediction based on the activation. We know predicting part is the inference part, right? The inference just forward propagation. So the prediction is largely dependent on the value of the activation. So let's see the activation for the two samples, the clean sample and the adversarial sample. So here is the activation of the clean sample. So here is the activation of the adversarial sample. So what's the difference between them? Clearly, very easily, you can get the difference between them is this, right? Because you just use this equation to do the dot production between here and here, and then you get this equation. So now we get the difference between the activation of the two samples. If we want to make the machine learning model confused, we want to maximize this guy, right? We want to maximize the difference between them, right? Between this guy, between the activation of this guy and activation of this guy. So we want to maximize this guy. On the other hand, we want to cheat a human being, right? How to cheat a human being? We should minimize this guy. If we can, we want to minimize eta so that we can cheat a human being. So if every element of eta is tiny, and for human beings they cannot tell the difference. So how can we do that? I think the idea is simple. We just pick eta equal to epsilon times the sign of W. So two parts. First part, because we want to maximize this guy, we just because it's dot product, right? We just get the sign of W, and at the same time we want to minimize eta. So how to minimize? We use a sign because it's just +1 -1, and we times the epsilon. It's a tiny, it's a very tiny number in this numerical system. So in this way, we can minimize eta and also maximize this guy. Okay. So now let me give you more notation. So here M is average magnitude of each element in W. We know W is an n-dimensional vector, right? So this guy is roughly eta times m times n, right? It's this guy. I mean the difference between the activation of x and the activation of x2. The difference between them is this guy, the dot product of W and eta. So now here is something interesting, because the infinite norm of eta does not grow with n, has nothing to do with n, right? So for human being, there are just many changes. We still can't tell the difference because each pixel, each element, the change is tiny. However, the machine learning model, they use different way to make prediction. So they perform for machine learning models, they probably only care about the value of the activation. By doing so, now the change in the activation actually is linearly with n, right? Can grow linear with n. So that means if we can have a high dimensional application, for example, many features in the input sample, or many parameters in the model, in this way n is very large. So this guy can be very large. If n is very large, this guy can be very large. In this way, the activation of x and x2, they are very different from each other. So the machine learning model should make a different prediction for that, right? Okay. So the takeaway here is, so even for simple linear model, we can cheat the machine. We can cheat the machine learning model. We can build a very high dimensional application to make the activation between clean sample and adversarial sample very different from each other, so that the machine model will give them different labels, different predictions. Okay, that's why, or why can't we cheat the machine model? Why can't we make them confused? Okay, I just finished the first part, how to I mean the definition of adversarial machine learning, why it's important, why can we do that. And now let's go to the second part, how to attack, which means how can we make machine learning model confused? How can we make them stupid? Let me introduce some techniques of attacking machine learning model. So how to attack is equal to how can we generalize adversarial samples? Because after we generalize some adverse samples, we can just give the machine learning model some adverse sample models, and hopefully they will make the incorrect prediction. That's the idea of attacking. So the most popular method so far actually is FGSM, first gradient sign method, which was proposed by Ingrid fellow in 2015. So FGSM actually is kind of a white box attack. I mean, later I will introduce black box attack, but for white box attacks, the idea is the hacker knows everything about the model. I mean, the attacker knows every parameter of the model, so has a complicated access to the model. So here, let me introduce another notation. JWXY is a loss function. Y is the correct label of X. So here, I also briefly go over the key step of SGD stochastic gradient descent, because for SGD we want to update the weights to decrease the loss, to minimize the loss, right? So we in SGD we compute the gradients to the weights, and then we use this part to update weights to minimize the loss, right? However, for here, because we want machine learning to make mistake, we want to maximize the loss, right? So we want to change minus to plus, because here is minimize the loss, here is maximize the loss. And also for LGD, we update the parameters, so we compute the gradient to the weights, right? But for here, we want to update the samples, right? We want to change the sample to get new samples. So we do the we compute the gradients to the data to the sample. That's the second difference. So in this way, we can generate our adversarial samples. I mean, if you give me one clean samples, I give you one adversarial sample by this FGSM method. Let me give you more detail. So here actually is a equation. So here is a noise vector. As I mentioned before, we want to get the size so that we can so that we want to maximize the change in activation and minimize the noise vector at the same time. So here just a tiny number for the numerical computing, and then we use the noise to update the clean sample. We get our adverse sample. We can see this algorithm actually very cheap, right? We don't need to update the weights or parameter. It's just only run one step. We can get the gradient and update the sample. Okay. Now let me give you more details about the example in the beginning. So here is image 1. Here is image 2. As I mentioned before, for image 1, it's just a regular image, just clean sample, our well-trained machine learning model. So here we use GoogleNet. It's probably the best model in 2015. So for well-trained machine learning model, very easily we can make the correct prediction for this one, right? It's Panda with a 60% confidence, roughly 60% confidence. But now we use FGSM method. We get the noise vector, and we put the we use noise vector to update the clean samples. Now we get the adversarial samples. Now we want to the same model to make prediction to this image. The adversarial sample clear easily. We can make the model confuse. The model actually predict this image is given, and also with a very high confidence, 99% confidence. That is stupid. Okay, so here why we use a eta of 0.007. Why we use this number? Because we know for this image, each pixel is 8 bits, right? 8 bits is 2 to the power of 8, 256. So the precision actually is 1 over 256, roughly 0.04. So we just want to pick a number close to 0.004. So we pick 0.007. Okay. That's an example of FGSM. Let me give you another example. So for here, let me give you 4 figures. So figure A, the weights of a logistic regression model trained on MNIST. Figure B, the sign of the weights of the model. So here, from figure B, you can see here's the white part, here's the black part. Because it's just a sum matrix, actually white part is positive, the positive number. The black part is the negative number. So from figure B, actually, you can see, because it's just a logistic regression model, actually this model has a low capacity and is fit well. However, the noise doesn't make any sense to human being, right? No pattern here. For here, the application, we want to tell the difference between 7 and 3. We want to tell the difference between 7 and 3 for this application. But here, it's nothing to do with 7 and 3. Right? So this figure doesn't make any sense to human being, because it has nothing to do with the relationship between 3 and 7. And figure C is a clean samples. For this one, I think the regular machine learning, a well-trained machine learning, will do a very good job. For example, even logistic regression model can have a low error rate, only 1.6% error rate for this one, because for human it's also very easy, right? 7, 7, 3, 7, 7, 3, 3, 3. For machine learning model, it's also very easy, very low error rate. And the figure D is the adversarial samples. Actually, for human being, I think it's still very easy. 7, 7, 7, 3, 7, 7, right? 3, 3, 7. However, for machine learning model now, it's very hard. So we actually use FGSM method to get a D from C. So now, even for C, machine model can get a low error rate, but for D, it gets a very high error rate, 99% error rate, which means only 1% accuracy. Okay, that's the second example of FGSM. Okay, so I just introduced FGSM. It's the white box attack. Actually, there is another approach of white box attack by the name of one-step target class method. Let me introduce this method, but before that, let me write the FGSM method formally. So here, y true is a true label. Let's have a look at this equation. It's just a rewriting form of FGSM method, right? I just changed the y to y true, right? And also I want to define the second thing, y target. So what's y target? Y target is something unlikely to be the true class for a given image. For example, give you a better understanding, y true. Do you remember the first image I showed in this lecture? It's a panda, right? So y true is panda. Y target can be a gibbon, can be a tiger, can be a rocket, can be a car, can be a human. So y target unlikely to be the true classes of a given image. For example, the panda image. So now we compute the gradient to the clean sample, but here is y true, here is y target. So actually they are in different, in opposite direction, right? So if we want to maximize the loss, to increase the loss, so for FGSM it's plus, right? But because this guy is in the opposite direction of this guy. So here, if we still want to increase loss, we should change the plus to minus here, right? So here is the key idea of one-step target class method. I think it's the key idea actually very similar to FGSM. But now here is one thing. So how can we get a Y target? How can we compute a Y target? There are two methods of computing Y target. The first method is by the name of step LL. So we can just get the least likely class predicted by Y target, right? You can just use this equation to compute the Y target. And the second thing actually is more interesting, by the name of step random. The author mentioned we can just random pick class as Y target. Why we can do that? The assumption is we have many classes. Like ImageNet has 1,000 classes or 12,000 classes. I mean, two different versions of ImageNet, right? So even for the small version of ImageNet, it has 1,000 classes. If you randomly pick class, you only have 0.1% chance it's a correct classes, which means you have a 99.9% chance it's incorrect classes, right? So which means you just need to random pick a class because very likely it's the incorrect class. So we assume in the future the machine learning model will have more and more classes. For example, 20,000 different classes or 1 million different classes. Very likely you just randomly pick one. Very likely you will get the incorrect classes. You can just you use that for Y target. Okay. I actually just introduced the white box attack, the FGSM, and the step LL and step random. For the white box attack, as I mentioned before, they know the model's parameters. However, there is another situation by the name of black box attack. So in this situation, the hacker, the hackers, they don't know the parameters of the model. They have no access. So they only have some idea of the domain interest. They only know it's a black box system. It's image recognition, or it's machine translation, or it's a self-driving car. And also, the number of queries should be limited. What's the meaning of this? The meaning is even it's a black box system, you can play with the system, right? But here, I mean by play with the system, I mean you can send a query to the system. However, the number of queries should be limited, because now even a very naive machine learning model, they should have some features to defend from the attack, right? If you send too many queries, probably very easy they can detect this. They can shut down system or reject your query. Okay? So for black box attack, if you want to play with the system, play with the machine system, the number of queries should be limited. So how can we do the black box attack? We have two limitations. First, we don't know the parameters, and secondly, we cannot play with the machine learning system, the black system, too frequently. Otherwise, they will reject our query. How can I do that? So let me introduce a technique proposed by paper note in 2017. Published the paper was published at Asia CCS conference. So here is the solution. The author actually proposed a new querying technique In this way, they can effectively get information from the black box decision boundary. I mean, they can just use the output label of the black box system to simulate the decision boundary, right? So, but we don't have the model, right? We don't have we don't know the parameters of model. How, I mean, for the methods like FGSM, if we want to generate the noise vector to generate adverse samples, we need the model, right? How can we do that? The idea is, if you don't have the model, you should train a substitute model. But we know nothing. How can we train a substitute model? Actually, in the paper, the author claims you just need to know the domain of interest. For example, if you know it's computer vision application, you may just pick a CNN, pick a ResNet, pick a efficient net to train. And hopefully we can make the substitute model work, and after that we can use substitute. We can do many iterations, and iteration we use substitute model gradient to get something like the noise vector in FGSM, and then use noise vector to generate the adversarial samples. Okay. So before I introduce the key idea, let me briefly review the Jacobian matrix. So for Jacobian matrix, it's kind of a generalization of the gradient vector. Let me explain. So here, assume we have a function from Rn to Rm. So for this function, assume each of its first order partial derivative exists on Rn. And because we want to do the partial derivative from each element of Rn to each element of Rm, so in total, Jacobian matrix is n by m, right? So here I give you an example of Jacobian matrix. So why we need to start that? Because it's a generalizing form of a gradient, right? For gradient, we just pick m as 1, right? So the gradient vector has the same dimension, the same size as the model. But for here, because black box attack, we don't know the probabilities of the output, right? So we have to deal with m different input rather than one input. Okay. So let me introduce the Jacobian data augmentation approach, as I mentioned. So here the target model we name it as Oracle. We refer to a target model, the machine model we want to attack as the Oracle model. We use a notation of O tilde. So because we don't know the probability of the output of the target model, right? We only know the output label, and at the same time we want to know to learn a similar decision boundary. So that means we have to make the substitute model has the same number of output labels as Oracle. In this way, we have to deal with n by m Jacobian matrix rather than a n-dimensional gradient vector, because we don't know probability. We should treat the output labels equally. For example, totally we have m output labels, we should treat them equally. Okay, we don't know the probabilities. So that's the reason why we needed to study the Jacobian matrix. So the next slide, let me introduce how can we finish the training of a substitute model and generate the adversarial samples. So for here, there are some notations. Again, the Oracle, which is the target system we want to attack. altitude and also the maximum number of epochs for this training, and also a substitute architecture F, and also an initial training data set as 0. So here, let me explain. So the attackers, they need to define architecture F. So here, for example, if you want to attack, you actually just need to have a high level knowledge of the application of the Oracle. For example, as I mentioned, so if you know it's a computer vision application, you can just use CNN, you use something like a ResNet or EfficientNet or GoogleNet. And also in the beginning, the attackers, so they need to collect a small data set. So here, for example, you want to attack, you don't need to know the distribution of the data. You actually just to find a representative input domain, and that's okay. So now let me go over the algorithm to show you the key idea. So first, as I mentioned, the input Oracle, number of epochs, the training data set in the beginning, and also lambda is hyperparameters. And we define the neural network architecture F, and for each epoch, we label the substitute training data set. We label the training data set. How can we label? We actually just play with the Oracle system, and we use output label for the each training samples of our initial data set, and then play with Oracle and get the label. We use this label as input sample. Okay. And also we train our neural network model, and we also want to generate adverse samples by the clean samples, right? So here we treat this guy as a clean samples. We want to generate an adversarial sample by these clean samples, and then we finish one training. We do the Jacobian-based data augmentation. We want to generate the noise vector, right? So here it's just like the FGSM method san gradient. But for here, we know the JF is a Jacobian matrix, not a gradient. So it's n by m. But the vector, the data is n by 1, right? So that means we need to pick one column of JF to use that column to generate the noise matrix. So which column we just need to use output label of the Oracle as a column number. So we pick the right column, and then we get the target gradient, and we get noise vector. We use noise vector to update the clean sample, and then we get a new adversarial sample. Okay. So let me give you a figure to visualize that. So the first step, and we need to collect the data in the beginning, and also we need to define the neural network architecture for the substitute model, and then we label a substitute model by play with the Oracle, play with the target system, and then we finish the one-step training, and now we have our model. We use the substitute model to generate the gradient, and then use the gradient to get the noise vector, and then we use the noise vector to generate one adverse samples by one clean sample. That's it for one iteration, and then we just do it many iterations. Okay, that's the key idea of black box attack. I mean, one approach of black box attack. There are also many other different approaches. Okay. So, but this one probably is the most famous one. Okay, but because we don't have enough time for for this lecture, we only focus on the white box attack. So I finished the first two parts. The first part, I introduced why adversarial machine learning important. How can we do that? And the second part, I introduced how to attack, how to generate adverse samples. So the next part, let me introduce how can we defend the machine learning model from attacking. So here the strategy is adversarial training. We need to use adversarial training to make the model more robust, to make the model better, and then we can defend. So but how can we do the adversarial training? So here let me give an example. For this example, let me define some notations. So here, clean means clean data. So ADV means adversary data. So L is loss function, M is batch size, key number of adversary samples in the batch, and lambda controls the relative weight of adverse samples in the loss, and T number of iterations. So for example, lambda equal to 0.3, M is 32, K is 16, T is 100,000. So by the notation, let me define the loss function. So here this part it's the loss function of the clean samples. So for this part, it's the loss. It's the loss function of the adversary samples. Okay. Now let me briefly go over the different steps of this adversary training. So firstly, at the first step, T equals 0, we randomly initialize W0, and for each step, we just read a batch. We just read a data batch from, for example, here M is 32. So we get 32 clean samples. We pick K. Okay, for example, here K16. We pick K16 clean samples. We use 16 clean samples to generate 16 adversarial samples by the current state of the model, which means the parameters at T step. And then we get our adversarial samples and clean samples. We use this loss function, clean sample and adverse samples to finish one step training and update the parameter to update the WT. Okay, so that's the idea of adversarial training. So now let me show you the effects of adversarial training based on FGSM. Yeah. Okay, so now let's have a look at the effects of the adversarial training. So I give you two figures. So the left figure is the baseline, the naive training. Clearly, it does not work for adversarial samples, right? Just like the panda example in the beginning, it has roughly 90% error rate. That's very, very high error rate, right? So the right figure is a model trained by our adversarial training method based on FGSM. So we reduce the error rate from 90% to around 18%. Right? So clearly, you can see the figures, they are very different from each other. So here we use a weight visualization of the maxed out networks trained on MNIST. So maxed out network actually was very popular in several years ago. So here each row shows a filter for a single maxed out unit. And from this figure, you can see the adversarially trained model actually more localized and interpretable. Okay. Okay. Let me also give you more data. So here is the effects, also the effects of adversarial training. Here, let me give you a table. The first row is the baseline. It's just baseline. It's just standard training. Here is adversarial training. For the clean data, I think both of them are very good. For example, baseline achieved the 94% top 5 accuracy for image data training with inception v3. And for the adversary training, it's also very close to 94% accuracy. The same thing for top 1 is also very good. So for these, they are adversarial samples. We change epsilon to get different adversarial samples. Now we can see something interesting. For the baseline, now the accuracy decreased from 78% to around 30%. That's ridiculous. Okay, and also for different adversarial samples, the accuracy actually, all of them, like accuracy is very low, right? So here it's only 27%. However, for adversarial training, you will see the accuracy is much better. Okay. And also the same thing for top 5. So here decreased from 94 to 60 and 55, 55, 57. But for the adversarial training, so its accuracy is very high, right? 92, around 92 and 91. So the first model, inception v3, is on ImageNet. So for the adversarial samples as ADV training, adversarial training is much better than baseline. So let's have a different model. Let's put 2 additional blocks to inception v3 to inception v3, and that give let's get a deeper model. So for this deeper model, I think the pattern is roughly the same. So for the clean data, high accuracy for baseline, also high accuracy for ADV training, adversarial training. However, for the adversarial samples, the adversarial training is much better than the baseline, right? So here accuracy decreased from 78 to 33, 30, 31. But for the adversarial training, this accuracy is very high, 75. So the idea here is so adversarial training can make the model more robust. It can achieve good accuracy for clean data and also for the adversarial data. But however, the baseline only achieve good accuracy for the clean data. It was totally confused on the adversarial samples. Okay. In this part, in this section, I just introduced how can we defend the attack. The idea is adversarial training. So the next part, let me show the idea of how can we effectively defend. Not only just make the model robust, can we make the model better? That's a question I'm going to answer in the next section. So let's go back to this table again. As I mentioned that before, so for the adversarial samples, the adversarial training is much better than baseline for the inception v3 and also deeper model, right? However, if you read this column carefully, you will find the baseline is always better than adversarial training. Top 1, this guy better than this guy, right? Top 5, this guy better than this guy. And the deeper model, top 1, this guy better than this one, and this guy better than this guy. So the takeaway here is the adversarial training will lose accuracy. Although it's not a significant loss, but always loss. That's a bad idea, right? Because we actually want to make it better, not only make the model more robust. We also want to make the model have a higher generalization performance to get a higher accuracy. That's our target for this section. So let me give you more results to visualize this problem. So here the horizontal axis B3 means efficient at B3, B7 means efficient at B7. So B7 is a larger model. B3 actually it's also a large model, but it's smaller than B7. So here vertical axis is the top line accuracy for the ImageNet, and the first bar is vanilla training, adversarial training, and also the mixed training. So for here, the vanilla training is just baseline, just 350 epoch training on the clean data here. So adversarial training means 350 epoch training on the adversary data. So the mixed training, which means the first half of the training is on clean data. It's on adversary data, and second half of the training is on clean data. So here you can see the vanilla training is better than the adversarial training, right? For both B3 and the B7 model. And for the mixed training, so even it can be better than vanilla training on B7, but it's still worse on B3. So we need a new approach to make the model more robust. I mean, can defend the attack and also can improve the accuracy on clean data. That's a target. So before I introduce the method, let me briefly go over batch normalization. The BN actually an important topic in deep learning in the last few years. So there are many papers about BN, and many authors they show great experimental results about BN, and we know BN can improve the performance, in particular generalization performance. However, why BN work is still under discussion according to Wikipedia. So, for example, some people saw that BN can reduce internal covariant shift or ICS, and other people saw that BN does not reduce ICS. BN actually can smooth the landscape or loss function. So here this part of why BN work is out of scope of this lecture because we don't have enough time. But for here we just use BN. BN is good. Okay, let me briefly go over the algorithm about BN. If you want to know more about BN, you should read the papers. So for BN, so here X, so here X is the input. So B is base size. So here M, for example, M 32, M is 64, M is 128. So BN has two hyperparameter gamma and beta. For BN, we have a batch of input. So we can compute the average of them, right? And also we can compute the variance of them. And after we get the mean and variance, we can use mean and variance to normalize the input, right? We got this one. And after we normalize it, we can skew and shift, and then we get our output of BN. So let me give you an example here. So here I use, because for better visualization, I use a tiny base size 3. We don't do that in real world application, because for the real world application, if you want to use BN, you should use a larger base size, for example, base size 64 or 128, because we want to use the batch to estimate the whole distribution, right? So we don't use small batch. But for here, just for visualization, I use base size 3. So for the input, again, we compute the mean, we compute the variance, and then we use mean and variance to normalize the input, and then we do the skew and the shift, and then we do the skew and shift to process, and then we get our output, right? So here is ideal BN. So now, after we review BN, now let's go back to the question. So why adversarial training hurt accuracy and clean data? Let me briefly go over a recent paper by Xie, by Xie, published at the CVPR 2020. So I'm going to introduce a technique invented by Xie. So to answer to introduce the technique, let me answer the question first. So why adversarial training hurt accuracy? The reason is that the reason for the performance drop is mainly caused by data mismatch, according to this paper. Because we know adversarial training and clean samples, the adversarial samples and clean samples, they are from two different domains, right? So if we train one of them and then transfer learning to another, it doesn't work, right? Because they are from two different distributions, that can hurt the learning. However, if we can bridge this distribution mismatch, we probably can get more useful information for both of them. We can get useful information from both adversarial samples and the clean samples. So this way, we think we probably can avoid the performance drop. So how can we get valuable features from adversarial samples in a more efficient way, and also hopefully we can improve the generalization performance? So for here, BN is very important because we know Bayes normalization. Actually, BN Bayes normalization is an essential part for modern computer vision architecture. For example, BN normalize input features by mean and variance. But if we use BN, we know the input features of BN should come from a single or similar distribution, right? Otherwise, if we compute the mean and variance, the statistical estimate is not accurate. It will hurt our learning and also hurt BN. So to avoid this problem, the author proposed approach. The idea is disentangle the learning by a second BN. So the traditional BN, so we just mix the adversarial samples and clean sample together. We use one BN to process them. So we compute the mean and variances. That's not accurate. That can be a problem. It can hurt our learning. And now we have two BNs. Now the first BN and the second BN. We use the first BN, the mean BN, to handle the clean samples, and use the second BN to handle the adversarial samples. So by doing so, we actually can disentangle the mixture distribution, and in this way we can effectively get useful information from both the clean samples and the adversarial samples, and also our statistical estimation will be more accurate. Okay, the key idea is adding a second BN to process the adversarial samples. So let me go over the algorithm. So again, at the beginning, we need to, as the first step, we need to randomly initialize the model, and for each iteration, we read a batch of data. So here, for example, M is 32, and we have M clean samples, which we use the second BN, the auxiliary BN, to generate adversarial samples by the clean samples from the clean samples. And now we have M clean samples and M adversarial samples. For example, M32. We have 32 clean samples and 32 adversarial samples. So in total, it's 64 samples. And then we compute the first loss by the mean BN for the clean samples. And then we can compute the second loss on the second BN for adversarial samples. Then we just add them together as our loss function for this, and then we do one-step training. So the name of this approach is AdvProp. So AdvProp actually can effectively learn the information both from adversarial data and clean data at the same time. And because AdvProp is very effective. Later I will show you some good results. You may ask, what's overhead here? Because you add another BN, right? The overhead here is trivial, is tiny. So for the computation and the storage, because other than BN, all the other layers are jointly optimized for both adversary data and clean data, so that they can share the same parameters for most of the architecture. And here is an example for efficient B7. This approach, AdvProp, only added 0.5% more parameters than the baseline. Okay, so the overhead is tiny and trivial. Let me give you some results, exciting results of AdvProp. First is comparison between the baseline, the vanilla training, and the AdvProp. The horizontal axis is number of flops. They just want to use different number of flops to show different models. Actually, it's different models. The horizontal axis means different models. And the vertical axis is top accuracy on ImageNet training. So clearly, you can see for here B0, B1, B2, B3, B4, B5, B6, B7, there are different versions of EfficientNet. For example, EfficientNet B6 means B6 here. So from this figure, we can see that the AdvProp is better than the vanilla training for all of them. And so the first comparison is the AdvProp and the vanilla training. Second comparison is AdvProp and adversarial training. So AdvProp is also better than adversarial training here. So for example, the horizontal axis is different models, B0, B1, B2, B3, B4, B5, B6, B7. So the vertical axis is top one accuracy. So clearly you can see, so AdvProp is also better than the adversarial training. So okay, now let's have a look at those two interesting results for both of them. AdvProp is better. So why? So because AdvProp carefully handled the BN, which is an important part in this situation. So the takeaway here is carefully handling BN can be very important for training adversarial samples. Okay, so here the application ImageNet training with EfficientNet. Okay, I finished most of them for today's lecture. Let me give you a conclusion. So the conclusion here is the first. Let me give you a summary about this lecture. Firstly, I introduced what's adversarial machine learning and why it's important, why it's possible. Because in the future, machine learning system probably will be everywhere. So this, the technique in the lecture probably will mean a lot to you. Will mean a lot to your happiness, to your privacy, to your safety, and also the second part I introduced how can we attack. How can we attack means how can we generalize adversarial samples. So the idea is how can we make the machine learning model confused, make them stupid? I introduced a white box attack, like a first gradient sum method, FGSM by Ian Goodfellow, published in 2015, and also the black box attack. The idea is we need to build a substitute model because we don't know the parameters of the target model, right? The oracle. And the second idea is we need to use Jacobian-based data augmentation because we don't know the probabilities of the output. We need to deal with all the output labels. So it's a Jacobian matrix. And also, how can we defend the approach is adversarial training. By using adversarial training, we can make the model more robust, but it will lose accuracy on clean data set. So we need to make things better. So we studied the AdvProp. The AdvProp is this convolutional learning by introducing a second begin. In this way, we can not only make the model more robust, but also makes the model more accurate. Makes model has a better generalization performance. Okay, that's the all the details of today's lecture. So here is a reference. If you have time, I think you should read all of them. I only give you 4 papers. They are all very interesting, and I think easy to understand. First, a paper by Goodfellow about the fast sum method, fast gradient sum method, and also another paper by Goodfellow, and also the paper by Papernote. It's published in 2017. It's kind of good paper of black box attack, and also the revision paper, AdvProp. Okay, that's it for today's lecture. Please let me know if you have any questions. I'm happy to take questions. Thanks so much. Thank you for your time.